All right, so we are introducing the mean value theorem, which is one of our really big theorems that you're going to have to know for the AP test. We did IVT in chapter 2, intermediate value theorem. This is MVT. This will pop up on every AP test that you see. So the mean value theorem, what it does, like it says, it connects the average rate of change, which is a derivative idea, something we've been doing for a while, with the instantaneous rate of change. So average rate of change is like a secant slope. Instantaneous rate of change is a tangent slope. So this is like pre-calculus, calculus. We're going to make a connection between the two of them. So here's the theorem. So we start with this. If the function's continuous at every point on a closed interval, so it doesn't have to be continuous everywhere, just on a certain interval, and then differentiable on the open interval, then here's what we can say. There's at least one point C in the interval from A to B at which f prime of C is equal to f of B minus f of A over B minus A. Okay, so a couple things just to keep in mind. One point C would be an x value. So there's a certain x value on the open interval at which f prime of C, so that represents the derivative at C. So we're going to do like a geometric, sort of a graphical interpretation. So what this represents is the slope of a tangent line at x equals C, and then this ratio over here represents the slope of a secant line between A and B. So I'm going to set up a picture for you guys so you can see what this would actually look like. So if the hypotheses fail, meaning if your function is either not continuous or not differentiable, so I'm going to show you what we've got going on down here. So here's one that works. So I'm going to give you a little picture of what the theorem actually looks like, and I'm hoping that when you see it, it'll make more sense than just the actual written out theorem. So say we've got like a nice, smooth, continuous function. It's going to look something like this. And this you can draw literally anything you want. I'm just giving an example. So let's say we've got A right here, and then let's put B over here. So I'm going to set this up right now, the slope of the secant line between A and B. So here's f of A, here's f of B. We can draw a little secant line in between them. Secant line would look like this. So what my theorem is saying right here is that this represents the slope of a secant line. We're saying there's at least one point such that f prime is the same as that average rate of change. Or in other words, you would have a tangent line at some point that's parallel to this secant line, same slope. So somewhere, and you can just kind of estimate. I'm going to show you what this would look like. We can kind of just move until we can find a point. So it would be right around there that we would have a parallel tangent. So it's like this point approximately. And if you take a look at what that tangent line would look like, it would look like that, which is parallel to our secant line. So we're saying that we can find some point in between A and B whose tangent would be parallel to this secant. That's what the average rate of change theorem, the mean value theorem, tells us. Here's just one example of how it could fail. It could fail if your function is not differentiable. So let's take our classic non-differentiable function, the absolute value function. So it looks like this. And let's say that this is A, let's say that this is B. So here, here. This is the slope of the secant line. The slope of the secant line would be 0, but at no point is there a tangent line with a slope of 0. So that tells you that it's very, very important that our function needs to be both continuous and differentiable. Okay, so that's just kind of laying out exactly what the theorem tells us. Let's take a look at some examples. So this first example, we want to show that x squared satisfies the hypotheses of the mean value theorem. So here's what you need to do. First of all, we need to state that f of x is continuous and differentiable on that interval. This one we can actually make a broader statement and say that x squared is actually continuous everywhere. So we can say f of x equals x squared is continuous and differentiable everywhere. So we don't even need to specifically mention that interval they're talking about. We know that this is always a continuous function, and its derivative is 2x, and 2x is defined everywhere as well. So it's continuous and differentiable everywhere. Whenever you set up the mean value theorem, you have to make a statement about that first. You have to make sure the hypotheses are satisfied. Continuous, differentiable, at least on the interval that they give you. Continuous on the closed, differentiable on the open. And so what we're going to do is we're going to find the solution for C. So the way that this works, step one is to actually find the average rate of change. Okay, so we're going to set up f of 2 minus f of 0 over 2 minus 0. And just up here in the corner, I'm going to give you guys the tiniest little visual of what we're working with here. So there's our parabola. Here's 0, 0, and then let's say that that's x equals 2 right there. This is the slope of the secant line. Our mean value theorem tells us that somewhere between 0 and 2, there's an x value with a tangent that's parallel to that line. So that's what we're trying to find right now. So f of 2 would be 2 squared, f of 0 would be 0 squared, and then of course 2 minus 0 is 2. So the numerator is 4 minus 0. So this is saying this slope, the slope of this secant line right here is 2. And so my theorem tells me that I can find a value of C such that f prime of C is equal to 2. Okay, so this is what I'm trying to find right here. So I start by finding the derivative. If my function is x squared, my derivative is 2x. And I'm saying that there's got to be an x value such that the derivative is equal to the average rate of change. So I set this equal to this. Not a bad equation here. I come up with x equals 1. So that would be the answer. This is the one x value that satisfies the MVT. Okay, so let's look at another one. Example 2, we're going to explain why the conditions aren't satisfied. So remember, your two conditions are continuity and differentiability. Okay, so this right here, if we simplify this function up, remember this is not just an x. The square root of x squared is actually the absolute value of x. So that's what this is equal to. So let me show you just a quick sketch. Absolute value of x plus 1 is just the absolute value shape, but just moved up 1 unit. So my graph looks like this. Now, this function is continuous everywhere. It has a point of non-differentiability at x equals 0. So depending on what the interval was, if they asked you for an interval from like 2 to 5, you'd actually be totally fine here. It's the fact that this interval contains a point of non-differentiability. That's the issue. So we would say the reason that it fails to satisfy the conditions is because the function is not differentiable on the open interval. So on that open interval from -1 to 1, the function isn't differentiable on that whole interval. All right. This one right here, that's a piecewise function. So we're going to give just a quick little sketch of what that should look like. So the easiest thing to do is start by plugging these points in. So if we plug 1 in here, we get 4. So I know I'm going to have an open circle here. And then my x-intercept is 3. I'm sorry, my y-intercept is 3. I know that. And then we know what a cubic looks like. So it doesn't really matter. Just kind of give it the shape of a cubic, maybe something like that. And again, it doesn't really matter what the actual shape looks like. The important point is what happens at 1. So when I plug 1 in here, 1 squared plus 1 is 2. So I have a closed point right here. And then my parabola would kind of, it starts at 1, so it would kind of, whoops, it wouldn't connect there, but it would go off like this. So sorry, ignore that little point. There is a break in the graph right there, which means the function has a discontinuity. So I'm supposed to be continuous on this whole closed interval, but according to this, I'm not. So the function is not continuous on that whole closed interval. Okay, so that's our second example. Third example, an interpretation of the mean value theorem. They will do this on the AP test for sure. Ask you to kind of explain if the mean value theorem applies or not, and they get you to write down in actual sentences. So the mean value theorem says if a car accelerating from 0 takes 8 seconds to go 352 feet, its average velocity is 44 feet per second. So the average that you come up with, that's like the f of, so technically what we just found was f of 8 minus f of 0. So it's like the right-hand side of the mean value theorem that we just found. So f of 8, they said was 352. That's the position after 8 seconds. It started at 0. So they did this work for us. I'm just kind of showing you where exactly this came from. So this, in its interpretation, would be the slope of the secant line. So what this means, because acceleration is continuous, you couldn't have something that's non-differentiable or non-continuous, because you know the way a car works, it smoothly accelerates without jumping from velocity to velocity. So what this means in terms of the mean value theorem is there must be a time in the first 8 seconds where the instantaneous velocity is 44 feet per second. So again, all we're doing here is interpreting what the mean value theorem tells us. And what the mean value theorem tells us is that the average velocity is going to be equal to the instantaneous velocity at least 1 point. All right, so we got that. Example 4, we've got a setup, a chart, something like you'd see on the AP test. So this is a velocity graph. It's a continuous function. Notice they mentioned that. And so we've got all of these values that we can go off of. So it says from 0 to 60, must there be a time t such that the acceleration is equal to 1? Okay, so remember acceleration is the derivative of velocity. So basically they're asking us to do the mean value theorem. And so it would look like this. This is the same as acceleration. And they want to know if this is true. So they give us an interval. And so these values of the interval would go over here. So we're going to plug those in. So v of 60 minus v of 0, and then over 60 minus 0. And these values are going to come right off the table. So velocity at 60 would be 10 feet per second, minus velocity at 0 would be negative 20, and then over 60 minus 0. Okay, so what we come up with, this we've got 30 over 60, so we come up with 1/2. All right, so we get that somewhere between 0 and 60. So must there be a time where the acceleration is equal to 1? Not according to anything that we've seen. The average velocity is 1/2. So we would probably assume that somewhere we would get something equal to 1, but there's nothing from what we've seen. And they're never going to make you get super detailed and try to go like piece to piece like this. One thing we could do is kind of take a look at some of the different intervals. And this interval would actually be helpful to us. So if we look at that, we can find an interval from 50 to 60. So let's do the same thing, but with 50 to 60, kind of shrink down our interval a little bit. So if we plug these values in, v of 60 we know is 10, minus, and then v of 50 is 0. And 60 minus 50 is 0. So this comes out to be 1. So we did actually find an interval where the mean value theorem is going to apply. So must there be a time? And we can say that yes, there actually must be a time between 50 and 60. We can get more specific with that interval. So we can say yes, a of t will equal 0 at some point on 50 to 60. All right, and that's just a direct application of the mean value theorem. Okay, so the next thing that we're going to look at is some increasing, decreasing functions. So I'm going to give you guys like the theory behind it, and then we're going to do a couple of quick examples. Okay, so the official math definition. You guys should know what increasing looks like. You know what decreasing looks like, but here's the actual definition of it. So we say that a function is increasing if x1 being less than x2 implies that f of x1 is less than f of x2. So basically what this means is as you go up in x values, you go up in y values. That's what it means to increase. So I'll say that again. As you go up in x values, you go up in y values. So decreasing is just the opposite. Decreasing says x1 being less than x2 implies that f of x1 is greater than f of x2. Okay, so again, what that means is as you go up in x values, you go down in y values. And that's what it officially, mathematically means to decrease. Okay, so a couple of quick things real quick right here. Starting with the function being continuous and differentiable, there are usually those hypotheses that we have to meet. We've got two calculus definitions of what it means. So this is more like the arithmetic definition. Here comes the calculus definition of increasing and decreasing. So we can say if f prime is positive on a certain interval, then f is increasing. Okay, so on any interval, if you can find an interval where the derivative is positive, that means that your function is increasing on that interval. And we actually have talked about that a little bit before. And then switch things up a little bit. If your derivative is decreasing on an interval, what that means is that f is, or I guess, I'm sorry, if your derivative is negative on an interval, that means that f is decreasing on that interval. Okay, so we're going to use those definitions right now in our first example. So we're going to introduce the increasing, decreasing, and that's actually where we're going to start our video the next time. So when is this function decreasing? When is it increasing? What we want to find is when the derivative is positive and when the derivative is negative. So let's kind of relate these here. This means y prime is negative. This means y prime is positive. So we need to take the derivative and then we can find when it's negative and when it's positive. So just as a little backup here, let's just look at this function. So we should be able to answer it just by looking at the function and what we've always known about parabolas, but I'm going to give you the backup, the actual calculus work that you can show. So clearly our function is decreasing for all negative values of x, and then it's increasing for all positive values of x. So let's back that up. So we want y prime to know when it's negative and when it's positive, so let's start by finding y prime. I gave you a nice simple function just to start with here. So the derivative is 2x. So the way to find where it's negative and where it's positive starts with finding where it's 0. And then we're going to make a sign chart. It might look familiar from pre-calc once I get it set up. So we're going to start by seeing when the derivative is 0, and of course we can divide both sides by 2 and show that when x equals 0, my derivative is 0, which again we can back up by looking at the graph. So we set up a little sign chart. So we go on a number line, always label our number lines. This is a number line representing y prime, and we put the 0 right in the middle. So any points where your derivative is 0, you mark them on the axis. And then we basically just plug in a point. So you can plug in a point over here. So if you plug in anything less than 0, anything at all, you plug it into the derivative. If you plug in -1, -2, -3, you're going to get a negative number. So I'm going to label that anything over here, anything in this range would give me a negative first derivative. And then if I plug in something over here, 1, 2, 3, any test value that I plug in here would give me a positive first derivative. So I'm going to label that as being positive. Okay, so what my sign chart will tell me is when my function is increasing and when it's decreasing. So this whole range right here, I've got a negative derivative. So here's what I'm going to say. And this is going to be my interpretation part. We need to start doing this now so we can get really good at it by the time the AP test rolls around. So we're going to say y equals x squared is decreasing on, and then we're going to list our interval, everything less than 0. We always leave this open because it's not a negative derivative at 0, it's a 0 derivative at 0. And then we give our explanation, because y prime is less than 0 on that interval. Okay, that is a perfect explanation for the AP test. Concise, gets all the information that you need without over-explaining anything. And then we can do the right half of the number line. Y equals x squared is increasing on the open interval from 0 to positive infinity because, and then just swap your explanation, because y prime is greater than 0 on this interval. Okay, again, concise, to the point, gets all your information. Okay, so we're going to pick up with that one in the next video.